So I made a data set, so I'm not giving away the answers. Same type of thing for your applied problem this week. Between what two times has this car had the most significant acceleration based on the data? Remember, acceleration is the derivative of velocity. In other words, acceleration is the rate of change of the velocity. So acceleration tells us how fast our velocity is changing. So speed is almost the same as velocity. Speed is just the absolute value of the velocity. In this case, they're both the same because the car isn't going in reverse 70 miles an hour. That'd be crazy. So the speed is our velocity for this problem. They're going to be the same thing. And we want to find out the rate of change for between each time period. So to go from here to here, our acceleration was positive 10 because we changed 10 miles per hour. For here to here, our acceleration was negative 5 because our velocity changed by a decrease of 5 miles per hour. From here to here, that's another negative 5, I should say, because we went down for our velocity. From here to here, it's positive 20. Here to here, it's a negative 15. So between what two times is acceleration most significant? For the data set I made up, it looks like it's between 330 and 340 because we were positive 20. Now it's saying most significant. If you do this data set and you get like a negative 20, that's still the most significant because that's the furthest from zero. That's the most significant change. So for mine, it's 330 to 340. Excuse me. It's allergy season for me here in Maine. So to conduct calculate a left point approximation to estimate the area traveled by the car. Remember what the area under the curve tells you. When we find an integral, we're finding the antiderivative. So it's like you go a step up in this relationship chart. So our first function that we usually deal with, f of x, is location. I think there's a better word for that, but it's like your position after a certain amount of time. We could say f of t too instead of f of x, so that's fine. But, the derivative is velocity, and the second derivative is acceleration, and the third derivative is Isaac. No, it's jerk. Okay, but we don't do that too much in calculus 1. Okay, so the whole point of this is that we have velocity here, right? So if we find an area under the curve, it's like finding an antiderivative. So we're finding the change in location. We're finding differences in location. Okay. So you can make a quick sketch, and I'll just say 0 is time 0, 0, at time 3 o'clock, and then so 10 will obviously represent 310. So we can't find an antiderivative. Like we can't use all those integral tricks that we've talked about for finding tough integrals. 50 is at the end here, okay? Because we don't have a function, but we can still find the area under the curve using approximation methods. So if you plot all these dots, so 60 miles per hour, I'll just start that right here. This is 60. At 310, we're at 70 miles per hour, so here's 70, and here's the 10, so there's a dot right there. And then 65 miles an hour at 20, and 30 miles an hour is 60, 40, sorry, at 30 miles an hour at time 330, and at 340 we were at 80, so that'll be a dot up here. And then ran out of room, 350, we're at 65 again. Okay, so with a different color pen, the left point approximation method means for each of these intervals you got to draw a rectangle, but you use the left side, the dot on the left side, to make your rectangle. So there's my first one, there's my second one, there's my third one. This is supposed to be at 330, right? Yeah. Here's my fourth one, and then here's my fifth one. I've got 5 intervals, right? This is one interval. Whoops. This is, come on, pen. This is one interval, 2, just from 3 o'clock to 3:10, that's one interval. 3:10 to 3:20, that's 2. That's 3, that's 4. There should be 5 intervals, so we got 5 rectangles. So the left point approximation method, you just find the area of each of those rectangles. This is a 10 across and 60 high. So this is, we got 600 for the first one. Going back to what I said over here, that would seem to imply that we went 600 miles because we're talking about miles per hour, which can't be. We didn't go 600 miles in 10 minutes, right? So what's actually happening is that we have units that that conflict with one another. The x-axis is minutes, our velocity is miles per hour. So we want to convert this to miles per minute, or we want to convert the x-axis to hours. I think either one is going to be messy, so let me convert the x-axis real quick. 10 minutes, that's 1/6 of an hour, right? So this is in terms of hours, 0.16 repeating. Okay, so now we can calculate how far we've traveled in terms of miles. If you take this for your length for the width of the rectangle, and then the height is 60, that says we traveled 10 miles in the first 10 minutes. That's more realistic, right? So that's a killer in math. Sometimes we get caught up in those rules and we just keep studying, like, the chain rule, the power rule of differentiation, all these different integral techniques. But when you do a real world problem, just make sure to watch out for those units and check yourself, okay? Like that 600 miles doesn't make any sense. So we caught ourselves. We're like, oh, it's because we got minutes on the x-axis. So they're all going to be the same. They're all going to be 1/6, right? Because this is 10 minutes, 10 minutes. Luckily, we have equal integrals. So what we can do is multiply each. What was I going to say? Find the area for each rectangle like this, or I could just take 70 divide by 6, because that's the same thing as multiplying by 1/6, right? So in the second set of 10 minutes, we went 11.6 repeating miles. And then for this rectangle, that's 65 was our height. That's what that dot is right there. 65 times 1/6 is 10.83 repeating. And then what else have we got? What have I done so far? That one, I've done that one. Now I need to do this one. So that was 60 miles an hour. So 60 divided by 6, that's 10. We got 4, we got one last one. So this one is 80 for the height up here, because we use the left endpoint approximation method. So 80 divided by 6 is 13.3 repeating. So if we add those up, so I got 55.83 miles that we traveled in that time with our left endpoint approximation method. Okay, so watch out for those units, but then after that, you're just drawing rectangles correctly and finding the area of rectangles. That's all the left and right endpoint approximations are. So I'll start you off in the right endpoint approximation method. Over here in blue, this is how I draw my rectangles. For this interval from 0 to 10, I use the right dot on that interval to draw the rectangle. So this is what my rectangles would look like with the right endpoint approximation method. So those 5, and then you do the same thing. You find the area of those rectangles. And that's the approximation for the area of the curve. And then last question, are there any other variables the car insurance company would want to track in order to monitor the driving habits of an individual? So right now we've got acceleration. We track that. That's probably important. I think a person's more likely to get in an accident if they have significant acceleration frequently, right? Because they're probably not being too careful. They're flooring it. They're slamming on their brakes. Either one is not good for safe driving. Velocity, we obviously want to track to see if they're speeding. So this is open-ended. What else? What other numbers might an insurance company want to track on those apps in order to determine whether we're a safe driver?